Today's lecture would be the last lecture of unit number 4. Only one topic is remaining that I will cover in this lecture. See, what I am going to cover is this example. What does it say? If the rigid body with one point fixed rotates about the principal axis, then show that kinetic energy of the body and the magnitude of angular momentum are constant throughout the motion. I need to show that it is constant throughout the motion. Okay, so how will I do it? It is really simple. First of all, you should know the kinetic energy of a body. So we know that the kinetic energy of a body is represented by this, where Ixx, Iyy, Izz are nothing but the moment of inertia, and Ixy, Iyz, and Izx are nothing but the product of inertia. If you don't remember, that means you have not properly studied the theorem in which I have already proved the kinetic energy. See, here I have already proved. We have done the entire theorem in order to find the kinetic energy of a rigid body with one point fixed. In my previous lecture, I have completed this. So we had this equation number 3, which gave us the the kinetic energy of a rigid body which rotates with one point fixed, and we know that Ix omega x omega y omega z are the components of the omega vector, that is the angular velocity, and Ixx Iyy Iz. See, we had a matrix. After that we solved, wait a second, we had a matrix, if you remember, moment of inertia tensor. In the matrix we had some diagonal elements and all. So basically, yeah, this was the kinetic energy. Okay, so I'm going to use this equation because I need to show that kinetic energy is constant. This is what I need to show. So yeah, here I am. This is equation number 8, last theorem I have already taught you. So see, this is equation number 1 for this theorem. T is equals to half Ixx omega x square plus Iyy omega y square plus Izz omega z square plus 2 times Ixy omega xy plus 2 times Iyz omega y omega z plus 2 times Izx omega x omega z. So this is the kinetic energy, and in this theorem I need to show that this kinetic energy is constant. Okay, so we know that we will consider the case in which the body is rotating along the principal axis, and I know what is a principal axis. This also I have covered. So one more thing you should remember, that in principle, when I consider a body which is rotating along the principal axis, then the matrix, that is the moment of inertia tensor, in the matrix which corresponds to the moment of inertia tensor, we had only diagonal elements, right? See, if you don't remember, I will let you know. We had also completed this note that said that the moment of inertia matrix, if we are considering a body which is rotating along the principal axis, in that case only diagonal elements exist and the non-diagonal elements are all zero. In such cases only the diagonal element exists and the non-diagonal elements are all zero. In which case, in the case in which we consider that the rigid body is rotating along the principal axis. So even now also we will consider the same case, that the body is rotating along the principal axis. If the body is rotating along the principal axis, obviously the product of moment of inertia, or the product of inertia, that is Ixy, Iyz and Izx, these terms will not exist. So all these would be zero. We will only have 1 by 2 Ixx omega x square plus Iyy omega y square plus Izz omega z square. And I will name Ixx as I1, Iyy as uh, I2, and Izz as I3. Okay, and I will have this equation. I hope I am clear. I will have this equation. Okay, I have replaced all these things. Now, then in the previous lecture, I have also taught you about the torque. Remember? So we had three equations which gave the equations for torque. See, nx, x component of the torque, that is along x-axis. This is the component of the torque along y-axis. and this is the component of the torque along z-axis. So in a system which is free from torque, we have all this side as 0 and we had this equation. That means this equation corresponds to a system which is torque free. So this condition I will take, I will consider a system which is torque free. If I consider a system which is torque free, I will have this equation number 2. Euler's equation of motion of a rigid body will change, and this would be the Euler's equation of rigid body, because all this side would be 0, because on the right hand side we had torques, and we are considering a system which is free from torque. I mean, that is in the absence in the sorry rotation is there in the absence of torque. So I need to show that the kinetic energy is constant. Okay, so for that I will consider the Euler's equation, and I will consider that my body or the body is rotating in the absence of torque. So in this equation, what you do is multiply the first equation by omega x, the second equation by omega y, and the third equation by omega z. Okay. So if you multiply the first equation by omega z, first equation will become like this. If you multiply the second equation, it will become like this, and the third equation would be like this. Now you have to add all the three equations. Since right hand side is 0, therefore after adding right hand side would be 0, and you will come up over here. This is really simple. Now after that you will observe that I3 omega x omega y omega z, and here there is minus I3 omega x omega y omega z. So I this term will get cancelled. Similarly, all other terms over here will get cancelled, and we will get I1 omega x dot, I2 omega y dot, I3 omega z dot in pluses. I mean, I will come up to this equation. Okay, this equation is also really simple. After that, what you have to do is, see, if you think of this omega x into omega x dot. Okay, I will change it. So consider the derivative of omega x square. See, listen, what is the derivative of omega x square? Omega x square means omega x into omega x. If I consider the derivative of omega x into omega x, I will use the u into v rule. So what is it? Omega x into omega x dot plus omega x dot into omega x. Okay, the same terms are there. So finally I will get 2 into omega x into omega x dot. Correct? So d by dt of omega x square is nothing but 2 times omega x into omega x dot. So I want that. I will use that over here. See, so what they did is they wrote 1 by 2 over here so that it will get cancelled with the 2. And I know that I1, I2, and I3 are all like it is constant regarding time, because it will not change. I1, I2, I3, that is the diagonal elements, or the moment of inertia does not change with respect to time t when I consider rotation, correct? This also I have explained in the previous lectures. So now what I have, when I will solve this equation, I1 will come outside the bracket, and in fact outside the derivative function. So finally I will take the derivative of omega x square, and it is 2 times omega x into omega dot. I have already explained now. So this 2 and this 2 will get cancelled. Similarly over here and over here we'll repeat the same process. So this equation and the last equation is same. Okay, so this equation, because when you will solve this equation you will get this equation, so I am replacing this with this. Okay, you solve it, you will get to know. But this is the value of t, that me, and this 2 will get on the right side, so it would be 0. Therefore d by dt of t is 0. That means the derivative of kinetic energy with respect to time is 0. That means when the time changes instantaneous, that means when the time changes, kinetic energy remains constant. That is, kinetic energy is constant with respect to time t. Okay, so this was really simple. In the same manner, what the next thing that I have to prove is moment of inertia. The magnitude of, what I need to prove is the magnitude of angular momentum is constant. Okay, you know that angular momentum L is equal to I double dot into omega bar. This also have already proved. I double dot into omega bar. What is I double dot? I double dot is the moment of inertia tensor, and omega bar is the angular velocity. So I know L is equals to I double dot into omega bar. But I am considering the rotation along the principal axis. So in this matrix, that is in the moment of inertia tensor, the non-diagonal elements would be 0 because my rotation is along the principal axis. So only the diagonal elements would be there, correct? That means my moment of inertia tensor would be I double dot. If I will multiply it with omega x, omega y, omega z, I will end up over here. And this is nothing. We know that I dot dot into omega bar is nothing but the angular momentum. So this is my angular, not mine, this is the angular momentum, okay, of the body when it is rotating. So L bar is equals to this. Now L bar square would be L bar dot L bar, and you know the dot product of two vectors a dot a bar dot a bar, it is very easy. So I1 into omega x square plus I2 into omega y square plus I3 into omega z square. Okay, when you multiply, the I coordinate will multiply with the matlab, the coordinate of the unit vector I will multiply with the coordinate of the unit vector I, because when you multiply I dot j it becomes 0. See, you multiply, you'll get to know the dot product is really easy. You have done it in 12th standard already. So L bar square equals to L bar dot L bar, which is this equation. Okay. Now likewise, we had used equation number 2, right? In this theorem also I will use equation number 2, but instead of multiplying with just omega x, what I will do, see, I will multiply the first equation by I1 omega x1. I will multiply the first equation by I1 omega x, second equation by I2 omega y, the third by I3 omega z. Okay, and I will get these equations. One moment. I will get these equations I1 omega x into omega x dot. Okay, so after solving this, we will come over here, and you know that I1, I3, this and I3, I1, these terms will get cancelled. Similarly, these terms, basically all these terms will vanish, and I will have only all these three terms. So I have reached over here. In the same pattern, I will use this equation instead of this, okay, in the same pattern as I have done in case of kinetic energy. But this is nothing but L bar square, okay. That means the derivative of L bar square is 0. That means L has to be constant quantity. That is, the angular momentum of a rigid body is constant. So I'm done with unit number 4. You have to read. See, you cannot depend just on these notes. You have to study books also, and you have to study really well for your examination. And it's not the case that since the exam is just for MCQs, you will not solve the theorems, because all the MCQs would be from within the theorems. Okay, so you have to study the this thing also, theorems also. It's not that only you statements you will do, because most of the MCQs they will ask is from within the theorems. I have already shared with you the last year's question paper in the classroom app. You can just see, and you will get to know what type of questions they can ask. In the next lecture, I will start unit number 5.